Hi, Miss Goshorn. This is Galvin. Mike's filming, and here is our Mousetrap car. The build of the car is pretty simple. 4 wheels made of CDs, axles made of pins, and little holders for the axles made of the pin caps, so that the wheels can spin in place. The main physics behind our car is this mousetrap here that propels the car. What happens is we have a fishing line strapped onto the extended mousetrap lever, and what happens is we tie the fishing string to the back axle here, and then we rotate the back axle, and thus doing work and applying creating potential energy elastic in our car, so that when we release the wheel, the car will propel forward and the car will go. And so that's basically the design of the car. A lot of people did it like us too. So a few things that were different about ours is on the back wheels we have rubber balloons here to increase traction on the ground when the car actually begins moving. So with these balloons here, what happens is instead of initially when I release the back axle for it to propel forward, it won't just spin out in place and waste all that energy just spinning out rather than going forward. So with the increased traction, there's more grip on the ground, so it'll move forward rather than spin out. And you can see that's kind of like how car companies use rubber tires instead of something less traction-y, like rubber or something for their wheels. They like plastic or something. They use rubber because it grips harder on the ground. And we didn't put that on the front axles because it was unnecessary to put balloons on the front axles, because only the back axles were actually moving forward. So thus we only need to put it on the back axles. We used the frame here is made of wood. It's a light stirring stick rod wood that we used. It wasn't a dense metal or anything, because with a lighter wood the entire car weighs less, so there's less inertia. And according to Newton's first law, inertia is a tendency for an object at rest to stay at rest, and unless acted on by an unbalanced force. And an object with more inertia will take more force for it to finally move. Also, another thing that's unique to ours is we extended the mousetrap lever arm here for 2 reasons. One reason is that with the extended arm, it makes the car have less force over more time. So instead of just one big quick snap with a lot of energy that could cause the car to spin out, we have it with the extended arm. It makes the force be less over a longer time, so it's a more continuous movement. Also, with the longer arm, we can make a longer fishing string here, and with the longer fishing string we can attach it onto the back wheel, and then while we're propping up the string we have more rotations right here, so the car can have a longer traveling distance. And Michael will now talk about the torque involved in the car.
At first we were thinking about applying a small gear on this axle right here, and then having a second axle which we would apply the fishing string to the rotational energy on behind it, with a bigger gear, turning the smaller gear to get more torque, but the mousetrap just did not provide enough torque to get that moving correctly, so we just simplified it and had a direct attachment of the fishing rod to just the wheel axle.
And then it would spin backwards when we let it go. So in class we took a couple measurements on this car, and on the force plate it weighed in at 3 newtons, so our mass was 0.3 kilograms. And in our trial run in class, we went 5 meters in 3.86 seconds, and we traveled a total of 13.75 meters in 15 seconds. And here I drew the position time graph for the car's movement. And I'm not sure, can you see that? Yeah, all right. So basically, when we released the car, it slowly started accelerating at a constant rate, increasing its velocity, and then achieving max speed somewhere around this point, and then it would slow down. So this shows why the position time graph looks like that. And we have a couple points labeled out, like 3.86 seconds for when the car traveled 5 meters. And we calculated average velocity between the point 0, the initial starting, and this point, 3.86 and 5 meters over here. And we calculated average velocity as the slope of the position function between those 2 points, and that equaled 1.2953 meters per second, which means on average between time equals 0 and time equals 3.86 for our car, the car was going an average of 1.2953 meters per second. And then using that knowledge, we can draw the velocity time graph here. And just like in the position time graph, the velocity time graph, it increased to the max velocity at some point, and then it decreased back down to 0 when the car finally stopped moving. And I have the same point labeled 3.86 meters per second using and the corresponding velocity here. And how we figured this velocity out was we knew at 3.86 seconds the car had traveled a total of 5 meters. So using the integral relationship between velocity and position, we know the area under the velocity curve equals position. And we know at 3.86 seconds the area is 5 because the car had traveled 5 meters. So we can calculate the velocity of the car when time equals 3.86, or when the car had gone 5 meters, by using the triangle area here and saying the area of the triangle here equals 1/2 base times height, and the height is velocity. So we can figure out velocity to be 2.5906 meters per second at that time 3.86. And we know the average velocity here is not the same as the average velocity that we calculated from the position function here is not the same as the velocity here, because the velocity here was at that specific time t, the instantaneous, not the actual average velocity between time equals 0 and time equals 3.86. And finally, using our velocity knowledge, we made an acceleration time graph. We assumed the car was moving in the positive direction, so as the car was speeding up, it had a positive acceleration. As the car was speeding down from the peak of its velocity part down, it had a negative acceleration. And using the same time value here, 3.86, we knew that, and the integral relationship between area and velocity, we know the area under the acceleration curve is equal to the velocity. So we know that the area here, which is 2.59, which is the velocity at 5 meters, we know 2.59 equals base, which is 3.86, times the acceleration, which is the height. And then we know that we solve for acceleration, we get 0.67098 meters per second squared at time equals 3.86 seconds. And now, using all this knowledge, we can plug it into the F equals ma equation that Michael will talk about.
Yeah, I got you. Here we go. This net force makes sense because Newton's second law states that F equals ma, and without a net force, an object at rest will not move, and an object in motion will stay in motion at constant velocity. But since we had friction on the wheels, it slowed down the vehicle until it decreased to at rest and just sat there at 13 meters.
Right. And then looking more closely at the calculations themselves, we know that F equals ma, the net force equals mass times acceleration. And at time equals 3.86, we calculated the acceleration to be 0.67098, and the mass was 3 newtons, which is 0.3 kilograms. So our net force was 0.201294 newtons, which was the force created by the mousetrap as it went backwards into the relaxed position after it was set to propel the car forward. And finally, one more thing, as we're looking from a momentum standpoint, we know momentum equals mass times velocity. So we know the mass is 0.3, and we know our velocity at time equals 3.48 equals equals what we calculated before right here, which is 2.59067. So we did 0.3 times that number, and we got the momentum to be 0.777 kilogram meters per second. And then knowing that, we know the impulse, because impulse is defined as the change in momentum. And initially we had 0 momentum because the car had 0 velocity, and then we ended up with 0.777 momentum, so we know impulse is 0.777. And finally, looking at the car's motion from an energy viewpoint, we can see that at the initial part, before the car was set and before it was just sitting there, the car had 0 energy inside the system. And us applying work, which is defined as F delta X, which is also just us rotating back that back axles to create the potential energy elastic needed to propel the car forward. That was the work that was being done. And after we add that work, the car is in the ready state, the position where if I let go, the axle will go forward. And that is completely potential energy elastic because it's related to a spring in the mousetrap, and that is equal to 1/2 k delta x, where k is the spring constant, x is the displacement of the string. And when we let go of the car, the potential energy elastic gets converted into kinetic energy, and at the instant before the car stops motion, it has kinetic energy completely. All of it is kinetic energy. So all that potential energy elastic becomes the kinetic energy here, and that formula is 1/2 mv squared, where mass is m and v is velocity squared. And that is it about our car. So hope you enjoyed the video. Thanks.
And that's it for our handwritten computations. Now begins the addendum that includes our computer software analysis part of the project. This year in physics, we also learned how to use video analysis software like Logger Pro and Tracker to acquire very precise data. Even though handwritten work can often be correct, it is always beneficial to have empirical data evaluated by a computer software program like Tracker itself. Looking at the position time graph here that we created using Tracker, we can tell that the car from time equals 1 to time equals 6 seconds moved quicker and quicker away from the origin in the negative direction. This was moving in the negative direction because when we established the axis in Tracker for the first time, we put the origin to the right of the car and the car moved in the left direction. Therefore, it was moving in the negative direction. The velocity is the slope of the position time graph, and the best fit line through this position time graph was x equals negative 2.211 t plus 3.49. And the slope here, negative 2.211, was very close to the speed we got using instantaneous speed at time equals 3.48 using our handwritten kinematics graphs, which shows how accurate and precise our calculations were, because even the computer program, using all its mathematical software and ability, computed a number very close to what we got. Now, looking at the velocity time graph we created using Tracker, we can see the trend in velocity of the car as it progressed from time equals 1 to time equals 6 seconds. The velocity graph here is roughly a negative linear function, which makes sense because we know from time equals 1 to time equals 6 by looking at the position time graph that the car moved quicker and quicker, which is correlated right here by the increasingly negative velocities. And the rate of change of velocity is equal to acceleration, and the best fit line through this velocity graph is v equals negative 0.75 t plus 0.128. The slope here, also the acceleration, is negative 0.75 meters per second squared, and this is very close to the acceleration we got using acceleration at time equals 3.48 via our handwritten kinematics graphs. So the velocity calculations and the position calculations we derived were both very accurate, both in our Tracker Pro as well as our kinematics handwritten graph. Finally, looking here at our acceleration time graph that we created using Tracker, we can see that the acceleration of the car from time equals 1 to time equals 6 seconds was roughly constant and had a slope of approximately 0, about 0.058. The best fit line through this acceleration time graph was a equals 0.058 t minus 1.021. And the slope here roughly equals 0 because our acceleration was constant during our test run. The velocity was changing, however, our acceleration was not. And as you can see in our graph, we have quite a bit of data fluctuation throughout our data collection values. And this was mostly caused by human error when me and Mike clicked erratically on our data collection, which caused the fluctuations here that you see. However, the slope remains roughly 0, and this corresponds with what we actually saw during our trial run.